Polymers. They're not just long, complicated words, they're the building blocks of our world. From the water bottles we use to the clothes we wear, polymers are everywhere. But here's the thing, not all polymers are created equal. Their properties like strength and flexibility depend on their size. And that's where our hero of the day comes in, gel permeation chromatography, or GPC for short. GPC is like a detective of the microscopic world, helping us unravel the secrets hidden within these long chains of molecules. Imagine a bowl of spaghetti, with strands of all different lengths. That's kind of what a polymer sample looks like at the molecular level. Some chains are short, some are long, and everything in between. Now, imagine trying to separate those spaghetti strands based on their length. That's essentially what GPC does, but with much more precision, and on a much smaller scale. Why is knowing the length of these chains so important? Well, it turns out that the length of a polymer chain, or its molecular weight, has a huge impact on its properties. For example, longer chains generally lead to stronger and more durable materials. Think about it, a thick rope is much harder to break than a thin thread, even though they're both made of the same material. GPC allows us to measure the distribution of molecular weights in a polymer sample. This information is crucial for understanding how the polymer will behave and for optimizing its properties for specific applications. So how does GPC actually work? Well, it all starts with a bit of chemistry. We take our polymer sample and dissolve it in a special liquid called a solvent. This solvent is like a swimming pool for our polymer chains. Now imagine this swimming pool has a special filter at the bottom. This filter is actually a column packed with tiny porous beads. When we inject our dissolved polymer sample into this column, the fun begins. The smaller polymer chains, being more adventurous, can easily enter the pores of the beads. They zip around, exploring every nook and cranny. Meanwhile, the larger chains, like giant cruise ships, find it difficult to fit into those tiny pores. They mostly sail through the column, bypassing the beady obstacles. As a result of this size-based separation, the larger polymer chains emerge from the column first, followed by the smaller ones. This continuous stream of separated polymer chains is then directed to a detector. This detector is like a watchful guardian, keeping a close eye on the exiting polymer chains. It measures how much of the polymer passes by at different time intervals. This generates a signal, which we can then plot on a graph. This graph, called a chromatogram, is like a fingerprint for our polymer sample. The chromatogram tells us how much of each chain length is present in the sample. From this, we can calculate important parameters like the average molecular weight, Mn and Mw, and the polydispersity index, PDI. These values give us a comprehensive understanding of the polymer's molecular weight distribution. But the story doesn't end there. GPC is not just about generating numbers, it's about understanding what those numbers mean for the real world. For example, a high PDI value indicates a broad distribution of chain lengths, which might result in a material with inconsistent properties. On the other hand, a narrow PDI suggests a more uniform polymer, potentially leading to a stronger and more predictable material. The applications of GPC are vast and varied. In the world of packaging, GPC helps ensure that plastic films are strong enough to hold our groceries, yet flexible enough to seal properly. In pharmaceuticals, it plays a critical role in characterizing drug delivery systems, ensuring that medications are released into our bodies at the right time and in the right dosage. To unlock the full potential of GPC, it's crucial to get the best possible results. This involves carefully choosing the right solvent and calibration standards. Regular maintenance of the GPC system is also essential for accurate and reliable measurements. GPC is more than just a technique, it's a gateway to understanding and manipulating the building blocks of our world. As we continue to explore the vast universe of polymers, GPC will undoubtedly play a pivotal role in shaping the future of materials science. From lightweight, ultra-strong composites for aerospace applications to biocompatible polymers for regenerative medicine, the possibilities are as limitless as the cosmos itself.